Hey folks, welcome to your second HL only video. By the end of this video, you will be able to find, so in this video we're going to talk about parallel plates, and by the end of this video, you will be able to figure out V, the electric potential, and E, the electric field, between a pair of charged parallel plates. So I want to start by talking about the equation for charge for parallel plates. So when you have two parallel plates, one of them is going to be gathering charge. So as you know, what's going to happen is our electrons will move, and we'll have a bunch of electrons all gathered together on one of our two plates. And so this equation on the page here tells you the amount of charge, what affects the amount of charge that will gather on one of those plates. So we know that Q is going to be the charge on one of the plates. And we also know, and so what you'll find is experimentally, you'll find that the charge that gathers on a plate is going to be dependent on the potential difference that's driving whatever circuit the parallel plate is hooked up to. So we've got our parallel plate hooked up to some kind of battery here. And the potential difference on that battery is going to affect how much charge can gather on one of our plates. Secondly, the area of the plate will affect how much charge it can gather on it. And finally, the distance between the plates is going to affect how much charge is gathered. And then all of these things are going to be multiplied by our constant, which we call the permittivity of free space. And it is going to have a value of 8.854 times 10 to the negative 12th. And our units here are going to be meters to the negative 3, kilograms to the negative 1, seconds to the 4th, and amperes squared. So let's go ahead and talk about E and V for parallel plates. And what I'm going to do is I'm going to go ahead and put a charge in between my parallel plates. So I know that there is an electric field between my plates, which I'm going to go ahead and call E. And actually, the electric field between my plates is going to be completely uniform. So I'm going to go ahead and draw that in with my field lines. And we'll have some curvature on the ends, but we're not going to worry about that. We're going to pretend this is kind of an infinitely long parallel plate. So we've got our point that's in an electric field, and our point charge here is going to have a charge of Q. So we know that the force on that charge is going to equal E times Q from the definition of an electric field. We also know that we can also figure out the amount of work that is done by the field. So we know that work is equal to force times distance. And so we can substitute in our equation for force, and we can say that work is equal to E times Q times however far our charge is moving in our field. So let me go ahead and I'm going to do something a little unexpected, and I'm going to divide both sides of my equation by Q. And what I'll get is that my electric field times the distance that a charge moves between my plates is equal to the work required to move that charge. But you should maybe, I hope, recognize this term here as the potential difference between your two plates. So what we'll get is that voltage is equal to my electric field times my distance, or electric field is equal to voltage divided by how far from my 0 volt plate I am. So that is to say how far my charge moves between my two parallel plates. And I can even add on to that, and I can say that my voltage over my distance is equal to my force divided by the amount of charge in my field. So the very last thing I want to introduce is the relationship between my electric field, between my plates, electric field, and sigma, which is the surface charge density on one of the plates, which is to say that is going to be basically how much charge you have per square meter on the plate. So remember from the very first slide, Q is equal to epsilon naught times voltage times area divided by distance. And what I'm going to do is I'm going to divide both sides of my equation by area. So what I get is that Q over area, charge over area, is equal to epsilon naught times voltage divided by distance. Q over area is going to be sigma, my surface charge density. And from the previous slide, we know that V over D is equal to my electric field. So sigma, my charge density, is going to equal epsilon naught times the electric field between the plates. However, our very first equation here is for the charge on one plate. But our electric field is between two plates. And so we're missing up here a factor of 2 because there are two plates. So sigma is actually going to equal 2 times epsilon naught times my electric field, or, as it is more commonly given, my electric field is equal to sigma over 2 times the permittivity of free space. So my electric field is equal to my surface charge density divided by 2 times a constant. So let's do an example. A pair of parallel plates are separated by 80 millimeters. A droplet with a charge of 11.2 times 10 to the negative 19th coulombs is in the field. Calculate the potential difference required to produce a force of 3.6 times 10 to the negative 14th newtons on the droplet. So let's start by listing out my givens. So first of all, I know that the distance between my plates is 80 millimeters, or 80 times 10 to the negative third meters. I know that my droplet has a charge of 11.2 times 10 to the negative 19th coulombs. And I know that I am trying to produce a force of 3.6 times 10 to the negative 14th newtons on the droplet. So those are all of my givens, and I'm now ready to write out my unknown. So my unknown, I can find in my equation, or in my question. I am being asked to calculate a potential difference, so my unknown is going to be my voltage. Let's go ahead and go forward now and figure out our equation. And so to do that, we're going to do a little bit of a multi-step trick. So I know that my electric field is equal to the voltage, that is the potential difference between my two parallel plates, divided by the distance by which they are separated, which is D. I also know that my electric field is equal to the force per unit charge between my two parallel plates. So I can go ahead and get rid of my electric field altogether, because now I have only my givens and my unknown in my equation. And I'm going to go ahead and solve for voltage, so that V is equal to force per charge times the distance between the parallel plates, which means that I am ready to substitute and solve. So I know that V is equal to F over Q times D, so voltage is equal to 3.6 times 10 to the negative 14th newtons divided by 11.2 times 10 to the negative 19th coulombs times 80 times 10 to the negative third meters. And when I stick that in a calculator, what I get is that the voltage required, the potential difference required, is 2,600 volts. And there you have it, folks. You have learned how to figure out how to use the relationship between voltage, electric field, plate separation, force, and charge to figure out different variables in our equations. So takeaways. The electric field between two parallel plates is uniform. The electric field between two plates is directly proportional to the voltage on the plates and inversely proportional to the distance between the two plates.